that when we compare the weir with the barrage, you see that we find the same components upstream and downstream for the weir and the barrage. Diversion headworks. The essential difference between the two is that in case of weir, you see that ponding is done by the crust and small portion or nil that is done by the shutter. But in case of barrage, you see that the ponding that is done by the gates. Otherwise, you can see that we have the same components. So these are diversion headworks that we studied so far, the components and their function purposes. Because these structures are constructed most of the time on pervious foundations, so different forces will be acting due to the surface flow and subsurface flow. So that's why we provide these protections to counterbalance those forces. So now we are going to study causes of failure of weirs and barrages on permeable foundations. That what can be the causes of failure when we construct weirs, barrages, dams, also other hydraulic structures on permeable foundation. So you see that the combined effect of subsurface flow and surface flow may cause the failure of the weir or barrage. Failure due to subsurface flow by piping or undermining by uplift pressure. So failure due to subsurface flow means that the water flow below the surface of the bed of the channel, the river, or we can say below the foundation of these structures. So the failure can result due to piping and uplift pressure. So we have to provide safety against these subsurface flow. And failure due to surface flow, that can be by hydraulic jump and by scouring. So we discussed briefly these failures, causes of failure, and how we can control them. So failure due to subsurface flow, the first is by piping or undermining. So I already explained this. At permeable soils, water seeps at the base of the weir and barrage. When the flow lines at the downstream end emerge at downstream end of the impervious floor, the hydraulic gradient may exceed a certain critical value of the soil. At this stage, the soil particles will be removed, because when the water is flowing beneath the foundation of these hydraulic structures, when the water is flowing, it will exert a force on the soil particles. That is known as the seepage force. So if this force is large enough, it will carry these soil particles along. So what happens is that when any hydraulic structure is resting on pervious foundation, the water flows below the foundation, and at this point at the water exit, if the force acting here, the seepage force, if it is strong enough, it will carry the soil particles along. So as a result, what will happen? This further concentration of the flow results more soil removal. You see, it will continue. This process starts at the end point and then it will progress towards the upstream. So as a result of removal of this soil, you see that a channel or pipe is created. That's why this is known as piping. So further concentration of flow results more soil removal. This process of soil removal further progresses towards the upstream and results in the formation of a channel or pipe under the floor of weir and barrage dam, also causing its failure. What will happen when the soil is removed beneath? So this will be settlement. Settlement will take place. So the stability of the structure that is in danger. This is known as piping or undermining. So how to control this? Providing sufficient length of impervious floor so that the path of percolation is increased and the exit gradient is decreased. As I already explained, that when we have only this as the foundation, that you only have this as the foundation, so what will happen is that this water, it will seep and it will appear here. But if we provide a sufficient length, for example, in this case here, that we provide a sufficient impervious floor, so this way the length of the seepage that is increased. This is desirable. Why this is desirable? Because the water is flowing, and as this length increases, what will happen is that at the exit point, the energy remaining in the water, that will decrease, because you see that at this point the water has maximum energy. This is full energy, 100%, as a result of this head. And as this water is moving, it is losing the energy, and at the exit point should be minimum energy as compared to the upstream, towards upstream points. So at this point, the energy that will be HL by H by L. You see the hydraulic gradient that we calculate, that is H by L. So the more is L, the less will be the value of hydraulic gradient. That is what we want. So to control this, provide impervious floor of sufficient length so that the path is increased, the seepage path is increased, and the exit gradient is decreased. And providing pile at downstream end. Why? You see now the importance of these sheet piles that we provide. If we provide a sheet pile here, then what will happen? This length will be further increased. You see now the water has to move like this and then exit here. Now you can see the importance of providing these sheet piles. So by providing pile at downstream ends. In any hydraulic structure, you see why this piping happens. Why this seepage of water takes place from this upstream to downstream. What is the reason behind this? In any hydraulic structure on permeable foundations, water flow from a region of high level to a region of low level beneath the structure. You can see that we have high pressure here and low pressure on the downstream. That's the reason why the water is pushed along here. When we store the water behind the dam, Same in case of weirs and barrages, we raise the water level upstream. You see, we have high pressure here and low pressure downstream. So this will force beneath the water to travel and appear as water here at the downstream. This is the reason why we have this piping phenomena that occurs if we have hydraulic structure on permeable foundations. So now you understand that this we cannot avoid, this will happen. What we can do is that we can control this. Clear? You can see this piping in this video here to understand the piping phenomena. So you see that we construct the barriers, dams for different purposes. Water use for agriculture, domestic water supply, industries, hydropower generation. So we have pervious foundation. You see high head to low head. So you see water will move. This is known as seepage. So as the water moves, it will also apply force on the soil particle. This is seepage force. So if the force is strong, it will carry the soil along, see? So you see a channel or pipe will form. So this is known as piping. You see the soil particle will be successively removed. So this piping will occur and this will result into, you see, structure can fail. Next we have failure due to subsurface flow. The first one we studied, piping or undermining. The second one is uplift pressure. So if the weight of the floor is not sufficient to resist the uplift pressure, the floor may burst and the effective length of impervious floor is thereby reduced. In this way, the final failure is due to reduction of effective length and consequent increase in the exit gradient. You see the combined effect is coming. All these forces will not act one by one. So example of such failure is Khan Ki Weir on Chenab. This was due to the uplift pressure. So this uplift pressure, you see that this is the uplift pressure that will act at the foundation, at the base on this structure because of the movement of the water. So we have water level here, that's why you see it is not zero. And we have more high water level here. So you see the ordinate is here more. So this uplift pressure for hydraulic structure where barrages or dams also hydraulic structure, this force will act. This is uplift pressure. Clear? And this will be equal to what? Let's say this is H. So it is pressure. So this will be equal to what? This will be equal to gamma H. P is equal to gamma H. Gamma of water. So how to control this? By providing sufficient impervious length and of appropriate thickness. Impervious length of what? The floor. by providing sufficient impervious length of the floor and appropriate thickness so that the weight of the floor is able to resist this pressure. Providing pile at the upstream end so that the uplift pressure is reduced. So you see that we have to provide a pile here. Now you can see the importance of these sheet piles that we provide. So as a result of what? This will reduce. This pressure now, it will be reduced. So providing pile at the upstream end so that the uplift pressure is reduced at downstream. The second one is failure due to surface flow. So that can be because of the hydraulic jump. We already studied this in detail in the hydraulics course. Same concept applies here. So the standing waves or hydraulic jump formed at the downstream of the weir barrage causes suction that acts in the direction of uplift pressure. Because of fast moving water, you see that this hydraulic jump, so it acts in the suction that acts in the direction of uplift pressure. If the floor thickness is not sufficient, it may fail by rupture. Example of such failures are Marala weir on Chenab and Rasool weir. This happened because of the hydraulic jump. So you can see that downstream, these hydraulic jumps are created, and if you remember, we have to provide the stilling basin concept that you remember that in case of hydraulic structures, we provide that. So here for barrages where we provide sufficient impervious floor of sufficient thickness to contain this hydraulic jump. So how to control this hydraulic jump? Providing additional thickness of floor to counterbalance the extra pressure due to the hydraulic jump. Constructing the floor thickness in one concrete mass instead of in masonry layers, so that we have a compact unit. So this is due to the surface flow. The structure can fail due to the hydraulic jump. And again due to the surface flow by scouring. So when the natural waterway of river is contracted, you see you reduce the width of the channel. The water will increase, discharge is the same, water velocity will increase because cross-sectional flow area is reduced. So water may cover the bed both at upstream and downstream of the structure. So the scour holes may progress toward the structure, causing its failure due to scouring. Example of such failure was Islam weir. So how to control this? Using the piles at the upstream and downstream ends of the impervious floor much below the calculated scour level. You see now the importance of these sheet piles that we provide. Let's say we have this as the impervious floor. So we provide piles here, sheet piles. That's why I told you these are basically protection works. So using piles at the upstream and downstream ends of the impervious floor much below the calculated scour level. So we discussed this already in detail. Providing suitable length and thickness of launching aprons at the upstream and downstream sides so that the stones of the apron may settle in the scour holes. So this again we already studied. So this is how we can control the scouring. So now due to the surface flow, we have the scouring and we have the hydraulic jump. And due to the subsurface flow, it can be due to the uplift pressure and due to the piping or undermining. So precautions against failure, we already studied this. Let us make a list of this again. The following precautions can be taken to prevent failure. The length of the impervious layer should be carefully designed so that the path of the seepage water is increased, consequently reducing the exit gradient. We already now discuss in detail these points. Sheet piles should be provided on the upstream side and the downstream side of the impervious floor to increase length of the seepage water so that the uplift pressure is considerably reduced. The thickness of the impervious floor should be such that the weight of the floor is sufficient to counterbalance the uplift pressure. Energy dissipator blocks should be provided. So you see that the blocks which you already saw in the figure previously, the baffle blocks, they are provided to dissipate the energy. Inverted filter should be provided with concrete blocks on the top so that the percolating water does not wash out the soil particles. And a deep foundation like well foundation should be provided for the barrage piers. You see this, I already show you. If I go back to that figure, so you see here a deep foundation that is provided for the piers. We have this inverted filter provided, launching apron against the scouring provided. These sheet piles, upstream, intermediate, and the downstream sheet piles are provided. So now you can understand that these are protection works. So we discuss theories of seepage. This is now for the subsurface flow of water. So we discuss the theories of seepage. These are very important to understand, and these theories of seepage help us to understand the pressures at different points below the foundation of the hydraulic structures, and we can accordingly design the hydraulic structures to counterbalance these forces. So hydraulic structures such as dams, weirs, barrages, head regulators, cross drainage works that later on we will study may be founded on an impervious solid rock foundation or on a pervious foundation. Impermeable may be also and permeable foundation, pervious foundation. So most of the time, because as I explained in the previous lecture that the river has the 4 stages that I briefly explained in the river stage. So in the river stage, you see we have solid foundation, rock foundation here, but we do not construct diversion headworks here because normally the agriculture fields are not here. And after that we have the boulder stage, where you see that large boulders will be there, submountainous area, boulder stage. Here we can construct the diversion headwork. And then we have the alluvial stage, alluvial deposits here in the river, the 3rd stage. First stage, the rocky or mountainous, then the second, submountaneous or boulder stage, then the third, alluvial plains. And then we have the delta stage, where you see these small channels, they supply water and join the ocean. So we studied there that normally here and at the delta stage, we do not construct the diversion headworks. So these 2 and 3 are feasible, but you can see here that at these, if we construct the hydraulic structure, there we have alluvial deposits. Mostly we will encounter this pervious foundation, permeable foundation. That's why we study these theories of seepage for hydraulic structures. Whenever such a structure is founded on a pervious foundation, it is subjected to seepage of water beneath the structure in addition to all other forces to which it will be subjected when founded on impervious foundation. So a structure which is founded on impervious foundation, forces will be acting. If the same structure is on pervious foundation, in addition to those forces, there will be seepage of water. So hydraulic structures founded on alluvial soil foundations do allow seepage below them. So the water seeping below the body of the hydraulic structure endangers the stability of the structure and may cause its failure either by piping or uplift pressure. Now we already studied that what is piping and the uplift pressure. So the above concepts of failure of hydraulic structures due to subsurface flow were introduced by Bly based on experiments and the research work conducted after the failure of KHALEEL in 1895. After the failure of KHALEEL in 1895, research work was conducted, experiments were conducted. Why? Because this was designed on experience and intuition without any rational theory. KHALEEL was designed based on experience. So experiments were conducted to find out what are the causes of failure so that in future we can have more stable structures. So Bly, he studied these and he come up with what is known as the Bly's creep theory for seepage flow. So he developed this theory around 1910 and he has written a book also on this. So he developed this Bly's creep theory for seepage flow. So what is this theory? According to Bly's theory, the percolating water follows the outline of the base of the foundation of the hydraulic structure. This theory says that water will follow the bottom contour. You see, in other words, water creeps along the bottom contour of the structure. For example, we have this structure here. We have this impervious floor. And we have this water. So this theory says that the water seepage path will follow the bottom contour. It come here, then it will follow the bottom contour. And it will appear here. This is what this theory says. For example, if we have sheet piles, let's say this is the impervious floor. and this is the depth of water, and we have these sheet piles. Then how the water will follow? So according to this theory, it will follow the bottom contour. Water will come here, then come here, then it will follow this line here, the bottom contour. This is what this theory says. Now this is assumption. We will later on see that this is correct or it is not correct. We will see later. But this is actually the assumption in this theory, that the seepage water will follow the bottom contour of the structure. The length of the path thus traversed by the water is called the length of the creep. So this total length which is traversed by the water, this is known as the creep length. You add this total length, horizontal, vertical. This is known as length of the creep. Further, it is assumed in this theory that the loss of head is proportional to the length of the creep. This theory says that if this is h, so this theory, and the total length of the creep is L, so this theory says that h is proportional to L. L is proportional to h. H is proportional to L. This is what this theory says, that it is proportional to creep length. If h is the total head loss between the upstream and the downstream, and L is the length of the creep, then the loss of head per unit of creep length, that will be h by L. This is the hydraulic gradient. So the hydraulic gradient, that will be h by L. This is called the hydraulic gradient. Further, Bly makes no distinction between horizontal and vertical creep. This is again another assumption. In this theory, he says that, you can see in this figure, we have this vertical creep, vertical, then again goes vertical, then horizontal, then vertical down, then vertical up, then horizontal, then vertical down, then vertical up. So it means that this L is basically summation of the horizontal creep plus the vertical creep. So he give equal weightage. Here the multiplying factor is 1, here it is 1. So no distinction between the horizontal and vertical creep. So these are basically the assumptions in this Bly creep theory. We will see these assumptions are correct or not correct. So to continue with the Bly's creep theory for seepage flow, you can see here that we have this structure, and this is the hydraulic grade line. This is the diagram here, because of the seepage of water below the foundation. No cut-off walls. So length of the creep will be simply this L here. And if we have the sheet piles here, this is how the water will flow. Follow the bottom contour. Clear? Follow the bottom contour. And because of the sheet pile, you can see that the pressure is reduced. You see here it is further reduced. So this is what, according to the Bly's theory, the subsurface situation will be like this. Consider a section as shown in this figure here. Let H be the difference of water levels between the upstream and downstream ends. So water will seep along the bottom contour as stated by the Bly's theory. You can see shown by the arrows. This is how the water will move down. It will come here, move down, then move up, then horizontal, then move down, then up, then horizontal, again down and up, and then it will appear here, exit point. So it starts at percolating at A and emerges at B, starts at A and emerges at B. The total length of creep is then given by what? Just summation of these distances. So you see 2 times d1 because the water comes here and then goes here, 2 times d1. Then L1, this is L1, the horizontal distance between the two sheet piles. So we have this L1, then the water goes down and then goes up. So 2 times d2, then we have L2 here. So we have L2 and we have the water goes down and then goes up 2 times d3. So this is the total creep length. So we can simplify this L1 plus L2 and 2 times d1 plus d2 plus d3. So this, if L1 plus L2 is equal to B, it can also be written as like this. Now the head loss per unit length or the hydraulic gradient will be what? H by L. So this will be equal to H by L, and L is, this is what is the total creep length as we calculated earlier. This is here. Or you can write down this or this, same. So this will be the hydraulic gradient. So head loss equal to this will occur respectively in the planes of the 3 vertical cutoffs. You can see here that at this point, what will be the head loss? That will be H by L multiplied by 2 times d1. Then at this point here, it will be H by L into 2d2. H by L is the total that we do. Clear? Multiply by 2d2, that is the head loss here, and at this point it will be H by L into 2d3. What about L1, L2? Easy to understand. If you can see here that if I extend it here, so this point here, this will be H by L times L1. And if I extend it here, so this here, this will be H by L into L2. So this is how it says that head loss is equal to this at the corresponding points will occur. The hydraulic grade line can then be drawn as shown in the figure here. So you see, this is the hydraulic grade line here. Now with this understanding, we discuss safety against the piping or undermining in the Bly's creep theory. So according to Bly, safety against piping can be ensured by providing sufficient creep length. And this L is equal to C times H, where C is the Bly coefficient for the soil. So he said that you provide sufficient length to save the hydraulic structure against the piping. And Bly give values for this C in his theory for different types of soils. So different values of C for different types of soils are given in this table here. You can see here for different types of soil he gave the different values. And the safe hydraulic gradient should be less than this value. Why 1/18, 1/15, 1/12 and 1 by this? That the gradient at here that we discuss the hydraulic gradient, the values that we have. So that should be less than these values. Less than 1/18, less than 1/15 for these type of soils to have safety against the piping for that structure. Now why 1/18? Because you see this L is equal to C times H. So now 1/C will be equal to what? H by L here. C comes here, 1/C, H by L. So this is the hydraulic gradient. You see we already defined H by L. So that is why this hydraulic gradient should be less than these values for these soils to provide safety against the piping. This is according to this Bly's theory. He gave these values for the C. And he stated that if you want to provide safety against the piping, the gradient in the hydraulic structure should be less than these values. So that is why it may be stated that the hydraulic gradient must be kept under a safe limit in order to ensure safety against piping. So in this case, seepage will take place, but the piping phenomena that will not occur, because in piping the soil is progressively removed. So because the gradient, the hydraulic gradient is below the critical value, so this piping will not occur. And Bly give these values for the Bly's coefficient, Bly's creep coefficient, Bly's coefficient. So based on this theory, from 1910 to 1926-27, hydraulic structures were designed based on the Bly's creep theory on permeable foundations. The second thing, safety against the uplift pressure. You see, we have uplift pressure and we have piping. So we have to provide safety against both seepage, subsurface flow. So the ordinates of the hydraulic grade line above the bottom of the floor represent the residual uplift water head at each point. So for example, if in any point the ordinate of hydraulic line above the bottom of the floor is 1 meter, then 1 meter head of water will act as uplift pressure at that point. This is clear, just like before I have detailed and explained, this is the same as I already explained. You have this as H. So we say that the uplift pressure here, this is also H. And then it will decrease because the water seeps, so there will be loss. And if we have some water here, then it will be trapezoid. If no water, it will become triangular. So you take from here, from the bottom, whatever, this is H here. This is the uplift pressure. that will act because of the subsurface water flow. If H dash meter is this ordinate, then water pressure equal to H dash meters will act at this point and has to be counterbalanced by the weight of the floor of thickness say T. So the uplift pressure that will be equal to P is equal to gamma H. So gamma W into H dash. Let me draw the figure so you can understand how this H dash now comes. You see that we have this floor here, and this floor has certain thickness, which is T. And below this floor is acting the uplift pressure. Let's say this is the uplift pressure, clear? Acting up. So this is the uplift pressure. This has to be countered by the weight of the floor. So that is say W, weight of this floor here. That can be of concrete. Now you want to calculate this uplift pressure, so it says that if H dash meter is this ordinate, then the water pressure equal to H dash meter will act here. But now we write down in terms of P is equal to gamma H, so gamma W into H, where gamma is the unit weight of water. So how you calculate this? You insert a piezometer here. How you will get this H dash? To insert a piezometer here, the water will rise, you get this H. That will indicate the P by gamma, as you studied in your fluid mechanics, piezometers. This is H dash. So gamma W into H dash, whatever the pressure here, that will act up. So this will be resisted by the weight of the floor. So the downward pressure that will be equal to gamma W into G in times the thickness, where G is the specific gravity of the floor material, can be concrete. So gamma W into that specific gravity, this is specific gravity into specific gravity, the unit weight of water. So this is multiplied by the thickness. Now for the critical condition, these two must be same for equilibrium. These two must be same. This is the upward pressure and this is the downward pressure due to the weight of the flow. So from here you see gamma W cancel, we get H dash is equal to G times T. Subtracting T on both sides, so we can simplify this, and from here T is equal to H dash minus T divided by G minus 1, and this can be written as H divided by G minus 1. And what is this H? H is basically the ordinate of the hydraulic grade line above the top of the floor. What will be H? If I go back to this figure, this will be H here. This is H. So we have this H dash that is equal to H plus T. So that is why H dash minus T can be written as H. And G minus 1 is the submerged specific gravity of the floor material. So this is the minimum thickness required because this is at equilibrium. Practically the thickness should be greater than this to provide the safety. So the thickness of the floor can be easily determined by this equation, and generally increase by 33% to allow a suitable factor of safety. So 4 by 3, 1.333, so 33%. This is multiplied here, so this will be then your T design. This is the thickness we need to provide safety against the uplift pressure. Now, it may be mentioned that the floor thickness has to be designed according to the above equation only for the downstream flow. Why? Because for the worst condition, that is when maximum ordinates of the hydraulic grade line occur, the water standing on the upstream floor more than counterbalances the uplift caused by the same water, and hence only a nominal floor thickness is required on the upstream side as to resist wear, impact of flowing water, etc. So you see that on the upstream side there will be already water here. So weight of this and weight of the water itself will try to balance the uplift pressure. So the equation that you provide the minimum thickness from here, considering the factor of safety, so that is for the downstream side, because here either the water level is very low or no water. So at this point here, the thickness you need to provide to counteract this uplift pressure here. So this is how you provide safety against the uplift pressure, by calculating the minimum thickness or the design thickness considering the factor of safety, and in the first part against the piping, that the gradient should be less than these values for safety against the piping or undermining. This was the Bly's creep theory. So in this theory, then we have certain limitations, and these limitations are that Bly made no distinction between horizontal and vertical creep. You see, we calculate the length, it was equal weightage, L plus H. According to Bly, the total creep length is sum of the vertical lengths plus sum of the horizontal lengths. Equal weightage factor, see, one here, one here. He did not explain the idea of exit gradient. He simply stated that the gradient should be less than these values for safety. Why exit gradient is important? Because you see the piping starts at the exit point and then progresses upstream. So that is actually the important point, and we need to calculate the critical exit gradient and then compare with the exit gradient to determine it is safe or not. Safety against the undermining cannot be simply obtained by considering a flat average gradient, but by keeping this gradient well below the critical value. So this is a limitation. Then no distinction between outer and inner faces of the sheet piles. In the Bly's theory, if you have this structure here and we provide these sheet piles, so no distinction here that this face is more effective, the outer faces, than the inner. So he give no distinction. We will study this in detail because we have other theories of seepage. We will see that the outer faces are more effective than the inner faces. But Bly creep theory does not explain that. So this is limitation. Or the intermediate sheet piles, where from investigation it is clear that the outer faces of the end piles are much more effective than the inner ones. So these limitations, when we discuss the other theories, automatically these will be clear. Loss of head does not take place in the same proportion as creep length. Clear? This was the assumption we already explained. He said loss of head is proportional to the creep length. So it does not take place in the same proportion as the creep length. The uplift pressure distribution is not linear but follow a sine curve. It is not linear, but it follows a sine curve. It is curved. Bly's does not specify the absolute necessity of providing a downstream sheet pile, whereas it is essential to have deep vertical cutoff at downstream end to prevent undermining. So he did not explain that this sheet pile is very important to be provided here. Because of this sheet pile, you see that the water creep length is increased, which is desirable to keep the exit gradient within safe limit here. So Bly's does not specify the absolute necessity of providing that downstream sheet pile. So these are the limitations. It will be further clear when we discuss the other theories. You will further see the clarification of all these points. So before we discuss the second theory, we solve this problem on the Bly's theory so that you understand how we apply the concept of Bly's theory. So this figure shows the sections of a hydraulic structure founded on sand. Calculate the average hydraulic gradient. Also find the uplift pressure at points 6, 12 and 18 meter. This is 6. Then we have 12. So this is 12 here, point B. And we have 18 meter. So this is point C, 18 meter. From the upstream end of the floor and find the thickness of the floor at these points. So what is the thickness of the floor here that is required? So we try to quickly solve this problem. So first part is that we calculate the average hydraulic gradient. That is the average hydraulic gradient. So in order to calculate this, what we need to calculate is that we will try to calculate the total creep length. So the total creep length in this case, total creep length so that will be equal to L. What is that? We have this 6 meter because the water will start here, seepage, and then creeping along. Then it will come here again 6, 2 times 6. So 2 multiplied by 6. Then it will cover this distance according to the Bly's theory following the bottom contour. So this will be 22 meter. So we have plus 22. And then it will follow this down 8 meter and then 8 meter here and will appear downstream. So we have plus 2 times 8. Here. So now the total length from here we can calculate. So this will be equal to 50 meter. And what is H? So H is equal to 4 meter. This is H. So the hydraulic gradient this hydraulic gradient is simply equal to H by L. So this will be equal to 4 by 50, and this can be written as 1 divided by 12.5. So if the soil is given, you can compare this, that it is within safe limit or not for the given conditions. So this is not given in the question, so we just calculate its value. Part B of the question is that we have to calculate the uplift pressure at point A, B and C. So we go for the uplift pressure at at 6 meter from upstream. That is point A. So now to calculate what is the creep length for A, you see that the creep length for A up to A. So it will be here 6, then 6, and then up to A it is 6 meter. 6 meter or how much? 8 meter. So this water comes here 2 times 6. And we have plus, this is actually 6, yes, 6. So this is 6. So this is equal to 18 meter. This is 6. 8 is this one, so this is 6. 6 meter. Then we calculate the unbalanced or residual head. Unbalanced or residual remaining, that is the residual head. Seepage head at A. So what will be that? The total head is H. This is H, and because of loss up to A, so that is H by L into LA. This is the head loss at A. So H minus this will give us the residual head, the remaining head. See, I explain here. Look, we have this as the total head. So this is H. Now as the water moves, this hazard is decreasing because of the losses. Let's say this is point A. So at this point there is loss of head. This loss of head we already discussed. This will be H by L multiplied by the creep length up to that point, which is LA. This is the head loss from this H. So what is the unbalanced or remaining? This is what? This is the residual remaining or unbalanced. And what will be this equal? This will be equal to H minus H by L into LA. This is how it comes. So just put the values, everything is known. We know H, clear, or this can also be written like this. You see, we have 1 minus LA by L into H. So now we can calculate this. Just you need to put the values. This will be equal to 1 minus, what is LA? 18. What is L? That is 50. And multiply by H, which is 4. So this comes out to be 2.56 meter. Now we have calculated this HA. This is actually your HA, small HA. Now we want to calculate the uplift pressure. The uplift pressure at A. So that will be equal to what? That will be equal to gamma H. So gamma W into this HA. Now gamma W is the unit weight of water. So this will be equal to 9.81 into HA, which we calculated 2.56. So this will be equal to, this is kilonewton, this is meter, and this is kilonewton per cubic meter. So from here the value comes out to be how much? 25.11 kilonewton per square meter. This will be the pressure, uplift pressure at A. We also need to calculate the thickness. So the thickness we can calculate according to the Bly's theory. We have the formula. So the thickness of the floor at A, that will be equal to 4 by 3 into HA divided by G minus 1, where G is the specific gravity of the floor material. This is the specific gravity of floor material. Now if it is concrete, so for concrete this can be equal to 2.4. So you can put here the T value, that will be equal to 4 by 3 into HA, that is 2.56, divided by 2.4 minus 1. So we get thickness as equal to 2.44 meter. This is the thickness at A. Similarly, you can proceed for B and C. Exactly same procedure. So you see that for point B, what will be the situation at point B? The creep length so that will be equal to 2 times 6, and up to B we have further 12 meter. So this is equal to 24 meter. Now the residual head that you can easily calculate, the residual seepage head at B, so that will be equal to HB. This will be equal to H minus H by L into LB. This is LB. You can easily calculate. And then the thickness, that you can calculate from this formula 4 by 3 into HB divided by G minus 1. So you can solve. This is just a repetition. You can solve. Now, because we have limitations of the Bly's theory, so we come up with the lens weighted creep theory. So Bly in his theory had calculated length of the creep by simply adding the horizontal creep length and the vertical creep length, equal weightage, thereby making no distinction between the two creeps. However, Lane, on the basis of his analysis, carried out about 200 dams. In some book it is 278 dams. 200 dams all over the world, stipulated that horizontal creep is less effective in reducing the uplift or causing loss of head than the vertical creep. So after studying more than 200 dams, Lane found out that horizontal creep is less effective in reducing uplift or causing loss of head than the vertical creep. Or vertical creep is more effective than the horizontal creep, because Bly gave equal weightage to both. So that's why you see this is his limitation of the theory. So therefore, Lane suggested a weighting factor of 1 by 3 for horizontal creep and 1 for the vertical creep. So the creep length according to the Lane's theory is then L by 3 plus V, where L is sum of all horizontal contacts and all sloping contacts having slope less than 45 degree, and V is sum of all vertical contacts, all sloping contacts steeper than 45 degree. So when give weightage to these 1 by 3 to the horizontal and 1 to the vertical creep, because he said horizontal creep is less effective in reducing uplift or causing loss of head as compared to the vertical creep. So the Lane's creep length is then calculated as, see here, D1 and D1 vertical, so weighting factor is 1. Now L1 is horizontal, so weighting factor is 1 by 3. Then a D2 and D2, so 1 weighting factor. Then L2, so you can see again 1 by 3. And D2 and D2, again the weighting factor is 1. So this is the creep length according to Lane's theory. This is the creep length, Lane's creep length. To ensure safety against piping, according to this theory, the creep length must not be less than C times H, where H is the head causing flow and CL is the Lane creep coefficient, and he give these values later on in this table for the C. is against the Bly's coefficient. Clear? So values of the Lane's safe hydraulic gradient for different type of soils. For different type of soil, Lane give these values for his coefficient. And then the gradient should be less than these values for safety against piping. For very fine sand or silt, less than 1 divided by 8.5. Then the structure will be safe against the piping. So for different types of soils. So what Lenz did is he just give weightage to the horizontal and vertical creep. The rest everything is the same as Bly theory. So Lenz theory was an improvement over Bly theory, but however was purely empirical without any rational basis, and hence is generally not adopted in any designs. Bly theory, though it is still used, even after the invention of another theory which is nowadays used, we will discuss in detail, that is the Khoslas theory. But Lenz theory is practically nowhere used and is having only theoretical importance. Although Lenz theory was an improvement, but because it lacked the rational basis, so it is not adopted for design of these hydraulic structures. The Bly theory, because he just give weightage to that, the rest everything is the same as per Bly's theory. So the Bly's theory was used from 1910 to 26, 27 for the structure. Some were successful, but larger structures, some structures were not successful. So then investigations were carried out, what is the problem, so that lead to what is known as Khoslas theory, and that is used for modern design of the weirs and hydraulic structures.